So this is the end. Oh, wait. There were questions in Alex that said round your answer to the nearest hundredth. You didn't understand those. Do you know, like, what type of question that was? Like, was it ones where you were, like, converting? Go ahead. Was it ones where you were converting from radians to degree measures? Okay, yeah, so I could do one of them. So, convert, so from radians. So let's say something like, was it maybe something like this? 3.5 radians, 2 degrees, and round to the nearest hundredth. Something like that. So are these the types? No. Okay. Do you happen to have one of the problems handy? 6 pi over 13. Okay. So we'll scrap this one. So, or actually, so convert 6 pi over 13 radians to degrees round to the nearest hundredth. So something like that. Okay. So remember the conversion factor, right? So remember our key from last time is that 180 degrees is equal to pi radians. So we're starting with 6 pi over 13 radians. And since we want to get to degrees, we're going to multiply. We want the degrees to be on top. So we're going to multiply by 180 over pi, right? So remember, if you're going from radians to degrees, you're multiplying by 180 over pi. If you were going from degrees to radians, you would multiply by pi over 180. Does that step make sense so far? Okay. So in this case, the pi's would cancel, right? And on the top, I'm left with 6 times 180 degrees. And on the bottom, I have 13. And so what I need to do in this case is actually just multiply those out. So if you take your calculator and you do 6 times 180 divided by 13, right? If you look at what your calculator gives you, it should give you 83.07692308 ... So it gives you some big long decimal. Does that make sense so far? Okay. So now all you have to do is round to the nearest hundredth. So remember, the hundredth place is the second decimal place. And when we're rounding, we always look at the previous number. So if this number here is 5 or bigger, we round up. And if it's smaller than 5, we round down. So in this case, it is, here I have a 6. 6 is bigger than 5. It's 5 or bigger, so we're going to round up. So this would be approximately 83.08 degrees. No problem. No problem. Did that answer it? Did that answer for you too? For everybody that had questions on that one? Awesome. Any other questions before we go on? The previous one, so like 3.5 or something like that. So same thing if I was going to convert 3.5 to radians. Okay, so it's the same deal. I'm starting with radians. So anytime I'm starting with radians, I'm going to multiply by 180 degrees over pi. So in this case, when I do this on the top, I end up with 3.5 times 180 degrees divided by pi. And so we're going to put that in our calculator. Now, when you put it in your calculator, so you could either use the calculator that's on Alex, or you could use your own calculator. But the important thing is you want to leave, the calculator has a button for pi, and that's the number, that's what you want to use. You don't want to use, I'll answer your question 1 second, Katie. You don't want to use the 3.14, because if you use 3.14, you're going to be off a little bit. So we're going to multiply this. So 3.5 times 180, and then if I divide that by pi, this would end up being 200.5352283. And again, we're trying to round to this decimal place here. I have a 5 in this decimal place, so we're going to round up. So 200.54. So does that help with that problem, Jelena? Okay. Katie, so in this problem, no, I meant convert 3.5. Oh, yeah, you're right. I did mean convert 3.5, not 2 radians, 3.5 radians, 2 degrees. I just wrote it quick. Sorry about that. Thank you. I thought you were asking. Yeah, I'm sorry. I thought you were asking something different. Any other questions? No? Okay. So then what we're going to do today is we're going to finish. There's one thing left for us to finish from section 6, or from section 4.1. And then we're going to do stuff from section 4.3. There were only 5 questions for this topic. Yes, there were only 5 questions for that topic. So it wasn't a ton of topics from section 4.1. Okay, so this is continued from 4.1. And we just have one other thing we're going to do. So once in a blue moon on Alex, you might get problems where they give you an angle and they want you, but they write the angle a little weird. They write it in terms of degrees, minutes, and seconds. So this is all about converting back and forth from decimal degrees to degrees, minutes, and seconds. Okay, so it's a little weird, and basically this is used sometimes like in navigation type things, and so it doesn't really show up that often. It's not something we're going to focus on this course, but once in a blue moon, Alex throws a problem in, and so I don't want it to throw you guys for a loop when that happens. So the thing is, what we're going to think about is we're going to think as if we have a circle, and our circle, remember, has 360 degrees all the way around. And so what we're going to think of is that 360 degrees, we're going to think it represents 360 hours. So it's kind of weird because I'm not saying like, oh, a clock, and a clock would represent 12 hours. We're just saying, oh, we have a circle, it's 360 degrees, and so we're going to think of 360 degrees as 360 hours. And so in that case, if you think about an hour, how many minutes are in an hour? 60, right. So in this case, when we're talking about angles in degrees, minutes, and seconds, 1 degree is going to be equal to 60 minutes. And then how many seconds are in every minute? 60, right. So 1 minute is equal to 60 seconds, which means 1 degree is equal to 3,600 seconds. And the reason why is because if 1 degree is 60 minutes, and then if you take those 60 minutes and each of those 60 minutes has 60 seconds in it, you would have 60 times 60, which gives you the 3,600. So these are the two things. And I'm like on a test, I'm never going to ask you about these. This is just in case it shows up on ALEX. So there is a objective on ALEX, a topic on ALEX that makes you like practice this, but I'm never going to like put this on a test or anything like that. So, but we're going to practice it right now just in case it comes up. So for example, convert 23 degrees, 42 minutes, 48 seconds to decimal degrees. Whoops. So again, I said it, but this symbol here is saying minutes, and this symbol here is saying seconds. So basically, I want to take the 42 seconds or 42 minutes and change it into degrees, and I want to take the 48 seconds and change it into degrees. So when we say 23 degrees, 42 minutes, 48 seconds, what we're really saying is 23 degrees plus another 42 minutes plus another 48 seconds. So I can just break it apart that way. And then what I'm going to do is I'm going to convert these two pieces here. So this is going to become 23 degrees plus, I want this middle piece to become degrees. So I'm going to use this here that says 1 degree is the same as 60 minutes, right? So this little symbol here is saying minutes. So we're going to multiply by, I want to get to degrees. So 1 degree over 60 minutes plus I have 48 seconds. And again, 1 degree is 3,600 seconds. So I want to get to degrees. So 1 degree divided by 3,600 seconds. So questions on where I got any of that before we work it out? No? Okay, so now I just have to figure out what this is. So if we work these out here, we're going to have 23 degrees plus this works out to be 0.7 degrees plus 0.01333 degrees. So if I add those together, we end up with 23.71333 degrees. And then, okay, I'll answer that 1 second. And then this 23, so depending on the problem on ALEX, like it might ask you to round just like those other problems did to the nearest hundredth or something like that. Okay, why is it always 360? It's just the way that we define that angle. 360, it has to do with the fact that there's 360 degrees in one whole circle. So we're equating a circle with being the same as hours. Does that help answer that question? No problem. Any other questions? So all you have to do with all these problems is basically whatever your problem is, if it looks like this, you would just replace these three things in my problem with what numbers you have in your problem. And it's the reason we kind of use the degrees, minutes, and seconds is because it's a little cleaner to say this than to say some big repeating decimal. That's really the reason why. It makes it a little nicer. oops, let me make sure you guys all see that. Going back the other way. So for example, convert 82.074 to degrees, minutes, seconds. So again, those minutes and second part. Did somebody have a question? No. I was going to say someone has their mic on, so if you just kind of check that out. So if you have a question, totally feel free, but otherwise if you could keep it muted just so we don't get all that feedback. Okay. So the degrees, minutes, and seconds, the minutes and seconds part, it's taking care of this decimal part. So that's the first thing I'm going to do here. I'm going to split this up into 82 degrees plus 0.074 degrees. And now what we're trying to do is we're trying to go back the other way. So just like before I multiplied, we're going to do the same thing in this case, except that this time I want to get rid of the degrees. So I'm going to put the degrees, 1 degree on the bottom, and I'm going to put the 60 minutes on the top. And so in this case, if I work this out, right, so if I take 82, so I have an 82 degrees, and then if I actually do this multiplication here, we're going to get to 4.44 minutes. Yeah, it's basically just the other way around. There is just one tiny little, like, slightly different thing that I'm going to show you in this next, well, in 2 steps from now. So right now, basically what I'm saying is I have 82 degrees plus 4 minutes plus I have 0.44 minutes left over. And so the thing that's just a slightly different this time is because I'm trying to go back to, I've gotten rid of my degrees. So I used 1 degree as 60 minutes. So now here I want to get rid of the minutes and turn these minutes into seconds. And so to go from minutes to seconds, so we have 82 degrees plus 4 minutes plus 0.44 minutes times 1 minute is the same as 60 seconds. Why did I put 0.074 times 60 over 1? Okay, because this time I'm not trying to, so it's already in degrees, but I'm trying to get to minutes and seconds. So I multiplied by 60 minutes over 1 degree because I have to get minutes into my problem. So my problem is asking about degrees, minutes, and seconds. Does that help? No problem. And then here I had minutes and I need to get to seconds. So that's why I use 60 seconds is the same as 1 minute. And so if I work this out, we end up with 82 degrees plus 4 minutes plus 26.4 seconds. And now we round the seconds to the nearest whole number when we're doing this. So basically this is saying 82 degrees, 4 minutes, 26 seconds. So we're stopping at seconds. Technically, like, you could break it down more into like all different types of seconds, like milliseconds and nanoseconds and all that kind of stuff, but we're not doing that. And again, this is not some major component of the course, so don't get hung up on this. This is just like the problems you're going to have to do in ALEKS are basically exactly the same as these 2 problems I just did. So just match them up. It's just to give you a little bit of practice, and so that if you end up seeing a problem that talks about degrees, minutes, and seconds, you can like change it to just to degrees. because what we're going to be dealing with in this course is all degrees or radians. In this case, you're actually not even rounding. You're almost basically called truncating. So all you're doing is you are just grabbing this part here, the 26. So we're just ignoring the decimal part, and we're just taking the 26 part, the second part. Does that make sense? No problem. Okay. So that's the end of section. If it were 0.8, would it still? Yeah, if it were 0.8, it would still be 26. So, yep. So it doesn't matter what it is after that decimal point in this case, because it's not rounding it. You're just taking the second part off. So, the rest of what we're going to do is section 4.3. And section 4.3 really gets at the heart of trigonometry, which is what Pre-Calc 2 is all about. And that's because we're going to learn what are these trigonometric functions. So this is section 4.3, trigonometric functions. And in this section, we're going to deal with them on a right triangle. So this is right triangle trigonometry. Okay. So when we're dealing with right triangle trigonometry, what we are doing is we're going to be looking at relationships in a right triangle. We are going to later on, so you'll notice I skipped section 4.2. We're going to come back and get section 4.2. Section 4.2 and 4.3 kind of talk about similar things, but from different perspectives. And I personally like to teach from section 4.3 first before I do section 4.2. So, if we have a right triangle, so all of the stuff we're going to be doing today starts with a right triangle. And we're interested in one of the angles in the right triangle. So in this case, I'm going to call that angle theta. And so, does anybody remember what the longest side in a right triangle is called? That side that's across from the right angle. Yeah, the hypotenuse. So this side here is the hypotenuse. And then we're interested in labeling the other sides, but we're labeling them from the perspective of theta. So this is a right triangle labeled from the perspective of theta. So here is my angle theta. So across from the angle, there's a side of the triangle. This side of the triangle that is across from the angle, that side is called the opposite side. And there's a side of the triangle that is touching the angle. And that's the adjacent side. Yep. So we have, there are 6 trig functions, and those 6 trig functions, so there's 6, and so when I say trig, we're really saying trigonometric, but we shorten it to trig. So 6 trig functions. And when we are saying that, when we're saying that there's 6 trig functions, these are relationships of the sides of the triangle. Okay, and so those 6 trig functions are, there's the first one, so I'm gonna put the name, definition. So there is the sine function, so S-I-N-E. And the way that we write that is sin theta is equal to the opposite side over the hypotenuse. So I'm abbreviating opposite as OPP and hypotenuse is HYP, and we will shorten the adjacent to ADJ just to save ourselves a little bit of writing. So the sine of an angle gives you the relationship of these two sides, the ratio of these two sides in the triangle. So the opposite side over the hypotenuse. The second one is called the cosine, and that is cos theta equals the adjacent over the hypotenuse. And then the third one is the tangent, so tan theta, and that is equal to the opposite over the adjacent. Questions? So no, you cannot use your notes on the test. So good question, but no. So the tests are no notes. Other questions? Okay, I'm going to give you something to help you remember which of these is what. So there's a mnemonic called so, ka, toa. So the so is sine opposite hypotenuse. The cosine is cosine adjacent hypotenuse. Tangent opposite over adjacent. So if you remember SOHCAHTOA, that can help you remember what the things are. Okay, so there are 6 trig functions, but I only put 3 up so far, right? And the reason I only put the first 3 up are because the other 3 actually are just these 3 trig functions flipped over. So the other ones are, so what goes with the sine is the cosecant, and that's CSC of theta is equal to the hypotenuse over the opposite. We have the secant of theta, so secant, SEC of theta, is equal to the hypotenuse over the adjacent. And then we have the cotangent, and so that's COT theta, and that is the adjacent over the opposite. And so the way that I remember what gets paired together, so for me, remembering tangent and cotangent are paired together and flip-flopped from each other, that's easy for me to remember. These other ones, I remember that my S here, sine, like each thing has to be mapped with a co-function. So sine goes with cosecant, and secant goes with cosine. The other thing to think of is this is an S, it's matched with a C. This is a C, it's matched with an S. So there's kind of 2 different ways you can think about that. Questions so far? No. Okay. So let's try some examples. So, for example, find the values of the 6 trig functions for theta. And so A is, here's my triangle, here's theta, and I'm telling you this side is 10, this side is 8, this side is 6. So we're looking to figure out what's the sine, what's the cosine, what's the tangent, and then what's the cosecant, the secant, and the cotangent. And we're going from the perspective of this angle theta. So this side here, that's across from the theta. This side is the opposite side. This side that is adjacent to the theta, that's the adjacent side. And then again, the side opposite the right angle is the hypotenuse. So we're going to find the sine of theta, the cosine of theta, the tangent of theta. And then remember, sine is going to get paired. We're going to flip it to get the cosecant of theta. We'll flip cosine to get the secant of theta. And we'll flip tangent to get the cotangent of theta. Can I go back one slide? Yeah. No problem. Okay. So back to the problem here at hand. Okay, so remember, sine is, we said, opposite over the hypotenuse. So what value is the opposite? 8, right? And the hypotenuse here is what? 10. And then I should reduce this, right? So 8 over 10, I can reduce that. 2 goes into 8 4 times, 2 goes into 10 5 times. So this is really 2 over 5. Oops, not 2 over 5, 4 over 5. Wrote the wrong thing. So what do we think the cosine is going to be? Okay, so almost, so we're right, the cosine, remember, is the adjacent, so it is definitely a 6 on the top, but it's the hypotenuse on the bottom, so it's a 10 on the bottom, so 6 over 10, and again, I could reduce this, 2 goes into 6 3 times, 2 goes into 10 5 times, so this is going to be 3 over 5. Do you have to reduce? So if you, I think in these problems, probably if you put it into Alex would say, hey, you can reduce it. You don't have to. Something that's easy to reduce, I kind of like to see it reduced. But if you have something you're like, I have no idea, like they're really big, ugly numbers, and you're like, oh, I don't know if this can be reduced. It doesn't matter. So in this case, I guess I would say no, it's just more about being able to find what the sine and the cosine and the tangent are. But it's nice to reduce if you happen to see that it's easy enough to do it. So in these problems, it's easy enough to do it, right? Because it's just everything's divisible by 2. Other questions? Okay, what about the tangent? What do we think the tangent's going to be? Yeah, so the tangent is the opposite, 8, over the adjacent 6. And again, I could reduce both of these by 2, so 4 over 3. So 4 over 3. And then to get the other ones, as long as I remembered what's paired with what, all we have to do is flip them over, right? So the cosecant is going to be 5/4. The secant is going to be 5/3. And the cotangent is going to be 3/4. And one thing I want to point out is that People get lazy and they don't write this theta here. They'll just write sine, S-I-N, or cos, C-O-S. You have to write a theta. You have to tell me the sine of what. It doesn't make any sense if you're not telling me what you're taking the sine of. So we're always taking the sine of an angle, and so we have to like write down what that angle is. So it's really important that you put that angle in. The very first school I taught at was a Catholic college, and so this joke went over better in a Catholic college, but I used to tell my students it's a sin to leave sine by itself, right? So you can't just write S-I-N and nothing else. Like, you're not allowed to do that. So you're not allowed to just write C-O-S, or you're not allowed to just write T-A-N. You have to have the sine of something, the cosine of something, the tangent of something, right? So yeah, so it's a sin to leave sine by itself. Kind of helps people remember that. Okay, that's a good question. So Braxton asked, my calculator shows sine to the -1 power. Would that be the same as the cosecant? No. So unfortunately in trigonometry, mathematicians, we do like this abusive notation. And so we're going to learn what sine to the -1 power is. It's actually the inverse sine function. So it's actually a completely different function. Your calculator does not have something to do with the cosecant, the secant, or the cotangent. So you have to remember to flip those over. And we will talk about inverse trig functions, but not yet. Does that help? No problem. Okay, should we try another one? So B. So this is theta, this is 17, this is 15. Okay, so in this problem here, 17 and 15, so this is what they gave me. So first off, like, can I just jump into doing the problem, you think? No, right. I'm missing something, right? I'm missing this side here on the bottom. So we need to figure out what this side is. Does anybody know what we could use that would help us figure out what this side is? Okay, so we could call it an x, sure, yeah. But there's a certain thing on right triangles. Yeah, the Pythagorean Theorem. Yep, so remember the Pythagorean Theorem says, and that's okay, I'm not good at spelling either, so don't worry. The Pythagorean Theorem says that a squared plus b squared equals c squared. And a and b are the legs of a right triangle. And the only important one that you have to like distinguish is c. C is the hypotenuse. So that's the thing we want to be careful of, that C is the hypotenuse. Okay, so you can call the missing side whatever you want. So if we want to call the missing side x, we can say here we have that x squared plus 15 squared is going to be equal to 17 squared. And if you were like, I would have put the x as the b, that's fine, it doesn't matter. As long as you get the c correct, that's the only one that matters. So questions about what I've done so far? No? Okay. So now I'm just going to work this out to figure out what x is. So we're going to have x squared plus 225 equals 289. I'm going to subtract 225 from both sides. So x squared is going to be equal to 64. And then x is going to be equal to plus or minus the square root of 64. So plus or minus 8. So for us right now, since we're just dealing with a random triangle and it's sitting just in space, we're just going to take the positive value. Later on, like next week, we're going to look at actually pinning our triangles into a coordinate plane, and then we might need to take the -8 as opposed to the +8. But for us right now, we just want the value. We don't care that it's negative or positive. So this side here is going to turn out to be 8. That's what we just found using the Pythagorean theorem. So questions on how I found the 8. If you have a question, you can throw it in the chat box. So now I'm in a position where I can find the other trig functions, right? So I can find the sine of theta, the cosine of theta, the tangent of theta, and then the cosecant of theta, the secant of theta, and the cotangent of theta. So the sine, right, what would the sine be? So the sine is the opposite, right? 15 over the hypotenuse, 17. What about the cosine? Yeah, the cosine is the adjacent, 8, over the hypotenuse, 17. What about the tangent? 15 over 18, right? So the opposite, 15 over 8 over the adjacent 8. And then to get the cosecant, secant, and cotangent, all I'm going to do is flip them over, right? So 17 over 15, 17 over 8, 8 over 15. Questions? No. It's not too bad, right? Yeah, so far so good. This section is actually fairly straightforward for the most part. So let's do another one here. So C. So this side is 8, this side is 7, and my theta this time is up in that corner. So again, I'm missing one of the sides, right? So the very first thing I'm going to have to do is, just like we did before, do the Pythagorean theorem to find that missing side. So a squared plus b squared equals c squared. And what should my c be here? Yeah, the c is the 8. So x squared plus 7 squared equals 8 squared. So x squared plus 49 is equal to 64. And then if I subtract 49 from both sides, we end up with x squared equals 15. So x is going to be plus or minus the square root of 15. So in this case, we're just going to take the positive one. So this missing side here is going to be positive square root of 15. You can't break down the square root of 15, but even if I could, I'm not going to. All right, so we're just going to leave it with the square root of 15 in it. Any questions on how I got that? No? Okay, so now, just like before, we're going to figure out the sine of theta, the cosine of theta, the tangent of theta, and then the cosecant of theta, the secant of theta, and the cotangent of theta. Okay, so now here's the important thing. Remember, it's always from the perspective of theta. So from the perspective of theta, right, this side here, the 7 is the opposite side, right? Because that 7 is opposite of the theta. And this square root of 15, that's the side that's touching the theta, so that's the adjacent side. So you have to be a little careful that you're looking at the problem how it's given, right? So you have to figure out what's the perspective of that angle theta. So in this case, what would then the sine be? Yeah, 7 over 8. What about the cosine? I know you guys are probably all like, I don't know how to write a square root in the chat box, right? You can just write square root of the number or SQRT and then the number. So it would be square root of 15 over 8. Because remember, the cosine is the adjacent, the square root of 15 over the hypotenuse, the 8. And I should have been careful and put the right angle in there. I didn't. And then the tangent is going to be the opposite, 7 over the adjacent, so over the square root of 15. So I know depending who you might have had for like Math 96 or Math 126, they might have really cared about you rationalizing denominators when you have a square root. I don't. I'm just going to leave it like that. I don't care that there's a square root in the denominator. It's 100% okay with me. I'll just leave the square root there. And then we can flip them over, right? So the cosecant would be 8 over 7. The secant is going to be 8 over the square root of 15, and the cotangent is going to be the square root of 15 over 7. Questions on that problem? No? Okay. I'll give you guys a minute to write this down, and then we'll go to the next example. Okay, so my next example says, suppose that the sine of theta is equal to 3 over 4 for an acute angle. Find the secant of theta. This should say actually for, let me put some room in here. Whoops. This should really say for an acute angle theta. Find the secant of theta. Oh, whoops. Okay. Yeah, and I don't know what happened there with my secant. I'm just going to rewrite that. Find the secant of theta. Okay. So this one, they didn't first give me the triangle, right? They just told me that the sine of theta equals 3/4. So the first thing I'm going to want to do here is actually draw myself a triangle. So I'll draw a right triangle with an acute angle. So here's my acute angle theta, and I have a right triangle. And they gave me information about the sine function, right? So the sine function, remember, we've been saying the sine is the opposite over the hypotenuse. So I happen to know what two sides of this triangle are, right? So the opposite side we know is going to be 3, and we know the hypotenuse is 4. So questions so far on how I kind of came up with my triangle. Okay, so now, just like in the other problems, I have to use the Pythagorean Theorem to find that missing side, right? So we have a squared, we have a squared plus b squared equals c squared. So we have a missing side, x plus 3 squared equals 4 squared. So x squared plus 9 equals 16. Oh, yeah, I know what you're talking about, Jade. So Jade asked, would the adjacent be 5 because of the, 3, 4, 5 triangle, like the special right triangle, 3, 4, 5? That's only if the 3 and the 4 are the legs of the triangle. So in this case, the 4 is the hypotenuse. So remember, the hypotenuse always has to be the longest side in the triangle. So this is not a 3, 4, 5 triangle, you're going to see. If the 4 was here, then it would be a 3, 4, 5 triangle. So we're going to subtract 9 from both sides. So if I subtract 9 from both sides, I get x squared equals 7. And then if I take the square root, x is going to be plus or minus the square root of 7. So this side here, we're going to make a positive square root of 7, our missing side. Question. Okay, so now we can find what we were looking for. So remember, we're looking for the secant of theta. So usually we get the secant by flipping over which trig function? Yeah, so we usually get the secant by flipping over the cosine. So remember, the cosine is adjacent over hypotenuse. So the secant is the hypotenuse over the adjacent. So in this case, the hypotenuse is 4, and the adjacent is square root of 7. So you could think about it, if you wanted to find the cosine first and then flip it over, you could do that. Or you could just think about, like I did there, oh, it's hypotenuse over the adjacent. Either one works. Questions on this one? No. Okay. So then, so I have one more problem and then one more other thing to talk about. So the last problem I have to do is actually a word problem. So I know those are everyone's favorites, and I know you're all probably going, no, they're not my favorite. I hate word problems, but it's going to be okay. So this word problem says a 12-foot ladder is leaning against a house and makes a 64-degree angle with the ground. Will the ladder, actually, whoops, not will. So, how high up the house will the ladder reach? Okay, so my general rule of thumb when we are talking about word problems is that when possible, draw a picture. So I'm going to draw a picture. So we have a house. Maybe our house has a door and a couple windows, right? Gotta make it a little lively, right? And so we have a ladder that's leaning up against the house. So basically, here is my ladder, and it's leaning up against the house. So here's the ground next to the house. Okay, so it tells me that the ladder is 12 feet long. So this side here, how long the ladder is, that's 12 feet. And it tells me that it makes a 64-degree angle with the ground. So they're talking about this angle here. So this angle here is 64 degrees. And we want to know how high up the house the ladder reaches. So we're interested in figuring out this distance here. So what do you want to call that distance there? We need to give it a variable. X. Okay. All right. So this is what I know about this triangle, right? I know the angle, I know 12, and I know X. And we can assume that our house is built really, really nice and that it's like a perfect right angle. The house and the ground make a perfect right angle, right? Probably houses and grounds are pretty close to making a right angle, and they should make a right angle, but you might have one that doesn't. But we're going to assume that ours does. So if you think about from the perspective of the angle, X is what side? So here's my angle 64. X is what side? Like over here, is that the opposite? Yeah, the opposite side. And then 12 in terms of my triangle is what? The hypotenuse. Okay, so I have an opposite side and I have a hypotenuse. So which trig function relates opposite and hypotenuse? The sine, right. So what we're saying here is that the sine of 64 degrees is the opposite x over the hypotenuse 12. Okay, now, sine of 64 degrees, that is just a number, right? Sine of 64 you could punch into your calculator and get a number. And so if I want to get the x all by itself, so what would I need to do to get that x all by itself? Yeah, I need to multiply both sides by 12 to move the 12 over to the other side. So 12 times the sine of 64 degrees is going to be equal to x. And so now all you have to do is punch that in your calculator. So if you punch 12 sine of 64, you should get x equals 10.7. Now, if you punch that in and you get, if you take your calculator and you do 12 times the sine of 64, and you're actually getting 11.04, it means your calculator is in radians, and you want to change it to degrees. And so just like I said last class, right, if you have any issues with your calculator, right, like bring your calculator and stick around at the end of any class and I can help you with that. But when you type it in as long as your calculator is in degrees, you should get roughly 10.7. I think I definitely rounded that, I believe. Yeah, so and I did it terrible. I should be a little careful. So it's like 10.7855 ... right? So technically, if we were going to round to the nearest tenth, it would be 10.8. So I should have been a little more careful when I wrote it down. Okay, so yeah, so if yours says 11, there's probably, it depends on what calculator you have. So we're not going to take the whole class time. So if you just hang out at the end and then you can tell me what calculator you have and I can help you figure that out. Other questions? No? Okay. And this is something that's actually going to come up in the next couple sections, and that is that there's two special right triangles that show up a lot for us in Pre-Calc 2. So, two special right triangles. Okay, so there is the 45 degree, 45 degree, 90 degree triangle. And there's also the 30 degree, 60 degree, 90 degree triangle. So these two triangles, how did we find out how tall the house was? Okay, so let me go back here. So does it make sense that I'm not trying to figure out how tall the house was. I'm trying to figure how high up the house the ladder reached. So I'm just trying to figure out not necessarily how tall the house is, where is the top of the ladder on the house. So that's that distance x. Does that make sense? No problem. Yeah. Yeah. So from this, you can't tell how tall the house is. You can't tell how tall the whole entire house is. You can just tell how high up that ladder is. Any other questions on the word problem before I go on? No. Okay. So, back here to my two special right triangles. So, excuse me. I have two special right triangles. And those two special right triangles are the 45, 45, 90 triangle and the 30, 60, 90 triangle. And these are special because the sides always have a certain ratio going on. So in a 45, 45, 90 triangle, I have the right angle. So this here is 45 degrees and this here is 45 degrees. And because the two sides are both 45 degrees, or the two angles are both 45 degrees, that means that this side and this side, even if my drawing doesn't exactly look at it, they're actually the exact same measurement. So whatever this side is, let's say this side, we'll call it x. This other side is also x. So those two sides are the same. And then if you use the Pythagorean Theorem to find the third side, you would find out that it ends up being x times the square root of 2. So for instance, if this was a 3 and this was a 3, you would have 3, 3, 3 root 2. Or 7, 7, 7 root 2. 100, 100, 100 root 2. So the sides are always in the same proportion. We in pre-calc 2, we use a 45, 45, 90 triangle a lot. And in the 45, 45, 90 triangle, when we do it, we actually usually worry about the way that we use it the most are when the two sides are a 1. So 1, 1. So if this is 45 degrees, 45 degrees. This side here would be 1 times the square root of 2. So just square root of 2. So you're going to see this triangle, this 1, 1 square root of 2 triangle show up a lot. Right? So I just kind of want to go over what these triangles are so that like next class when I'm saying, oh yeah, it's a 45, 45, 90, 1, 1 root 2, you're not all like, what? Where'd that come from? Right? So that's where this is. Questions? No. Okay, the 30, 60, 90 triangle. So, okay, so the 30, 60, 90 triangle, one of the angles is skinnier than the other. So 30, 60, 90. And this also has a relationship. If you look at the angles, so the angles here are 30 degrees, 60 degrees, and 90 degrees. 30 is the smallest angle, so the side across from the smallest angle, that is the x. The hypotenuse is always then 2x, and the side across from the 60 is always x square root of 3. So that's the relationship for the 30, 60, 90 triangle. And again, we often see it in our class as, so here's 90, 30, 60. We often see it as 1 time, 2 times 1, which is 2, and 1 times root 3, which is root 3. So we often see it as 1, root 3, and 2. So they're just two special right triangles that are going to show up a fair amount in our course. And I just kind of wanted to go over them today so that then next class when we use them, we're familiar with them. Questions? No? Yeah, across from the smallest angle, the 30 degrees is always where the 1 goes. So it's always across from the 30 degrees. Other questions? Okay, so that is where I was going to stop for today, and then we'll pick up with sections 4.2 and 4.4 next week. So remember, you have homework due on Friday, and the homework due on Friday is those 5 topics from section 4.1. And if you have any questions, you can feel free to stick around. If you need help with your calculator, feel free to stick around and I can help you guys. Otherwise, have a good rest of your day. You get out a little early today. Don't get used to it. It's not going to happen very often, but it will today. No problem. Have a good one.